Hi everyone, in this lesson you will learn about the acid-base property of salts. Please read the OER textbook chapter section 14.8. But before we learn about the acid-base property of salts, we will need to understand the relationship between Ka, Kb, and Kw first. We already learned from the previous chapter that when you have weak acid, when weak acid dissolve in water, it's going to transfer proton to water and become its conjugate base and also produce hydronium ions. The Ka expression for this reaction would be the product which contain the conjugate base and hydronium ion divided by the concentration of weak acid. In the absence of weak acid, when the conjugate base present by itself and is dissolved in water, this conjugate base can accept proton from water, behave as a base to produce hydroxide ions as well. And because this is involved with the base, so the equilibrium constant that we can write for this would be the Kb expression, which come from the product over the reactant excluding water. Recall from Chem 122, we learned that when we combine the two reaction equations together, the new equilibrium constant will come from the product of the two multiplied by each other. That means in this case, if I combine the reaction equation of weak acid ionization and the conjugate base ionization, you can see that when you combine them, you can cancel the conjugate base and you can also cancel its weak acid. If you look at the product of this combination closely, you will see that you will end up with two water ionized into hydronium ions and hydroxide ions. And this equation is autoionization of water. And the equilibrium constant for the autoionization of water is Kw, which is equal to the concentration of hydronium ions multiplied by concentration of hydroxide ions. You can review the concept of autoionization of water in chapter 14.4. And again, as I mentioned, when you combine the reaction equation, the new value of equilibrium constant will come from the product of multiplication between the two equilibrium constant. So that means in this case, the new equilibrium constant will come from the Ka of the weak acid multiplied by the Kb of its conjugate base. And you can see that you can cancel the weak acid and you can also cancel the conjugate base as well. So that means the product of these would equal to the concentration of hydronium ions multiplied by hydroxide ion, which is the same as Kw that we just mentioned. In conclusion, the Ka of the weak acid and Kb of its conjugate base is going to be related by the Kw. So that means the weak acid and its conjugate base again will be related by the Kw. And from the previous section, we learned that at 25 degrees Celsius, the concentration of hydronium ions is equal to 1.0 times 10 to negative 7 molar. Same as the concentration for the hydroxide ion at 25 degrees Celsius. Therefore, we can say that Kw would equal to Ka times Kb of the conjugate acid-base pair, which is going to equal to 1.0 times 10 to negative 14. Again, this number valid only for at 25 degrees Celsius. Or we can say that if you take negative log of all of these, you can also say that the pKw would equal to pKa plus pKb, which is going to equal to 14. Similar to pH and pOH, pKa and pKb is constrained by 14 at 25 degrees Celsius, which means that Ka and Kb of the weak acid and its conjugate base, they are inversely related by this 10 to negative 14. So that means if you have a high value of Ka, the Kb of its conjugate base will be very low value, vice versa. For example, this is the relative acid strength sorted by Ka value, ranging from high Ka value to a very small Ka value. The larger Ka tell us that When these species ionized in water is undergo dissociation a lot more than the one that have lower Ka value, it tells us that this water right here doesn't dissociate much at all at 25 degrees Celsius compared to the hydronium ions. Now let's compare this acid strength to their relative conjugate base strength. For example, if you look at hydronium ions, when hydronium ion lose a proton, it will become its conjugate base, water. And when chlorous acid give off a proton, it will become the conjugate base, chloride ion. Next, when you look at hydrofluoric acid, when it loses a proton, it will become its conjugate base, fluoride ions. You can see that the difference between the top chart and the bottom chart is that they are different by one proton. Again, conjugate acid has one more proton than conjugate base. If you go all the way to the end, which is water, the conjugate base of water is the hydroxide ions, because as water loses a proton, then it will become hydroxide ions. Now if you look at the Kb strength, you can see that the Kb strength is ranging from very low Kb strength all the way to high Kb strength. So if you compare between these two charts, then you will see that the Ka of the acid will be the opposite of the Kb of their conjugate base. High Ka value would give the low Kb value. In order for these two to multiply and equal to 10 to negative 14 at 25 degrees Celsius. So again, the relationship between Ka and Kb are inversely related. In summary, I can say that the stronger the acid, the weaker its conjugate base. Vice versa, the weaker the acid, the stronger its conjugate base. Note that this relationship applies to only conjugate acid-base pair. If they are not acid-base pair, this relationship will not apply. Now when we look at the strong acid, the Ka of the strong acid would be infinity. This is because strong acid completely ionized. So that means at equilibrium, all of the reactant will convert to the product, giving the Ka value to be a very large value to the infinity. So if we look at the conjugate base of this strong acid, then the Kb for the conjugate base would equal to Kw divided by Ka. Since Ka is the infinity value, the Kb value then will approach 0. This tells us that for the strong acid, its conjugate base will not behave as a base. It will behave as a neutral pH. Same idea applies for the strong base. For the Kb of the strong base, it will equal to infinity. So that means its conjugate acid, Ka, would also approach 0 as well. And we can say that for the strong base, its conjugate acid will not behave as an acid because Ka is equal to 0, but instead it will behave as pH neutral. For example, if you consider the strong acid, hydrochloric acid, when the hydrochloric acid, which is a strong acid dissolved in water, is going to dissociate completely to chloride ions and hydronium ions. One hit arrow of the strong acid tells us that the chloride ion would not recombine with the hydronium ions. In this case, the conjugate base chloride ion will not behave as a base. It will behave as pH neutral. Same for the strong base as well. The strong base, sodium hydroxide, once it's dissolved in water, it will dissociate into sodium ion and hydroxide ions. Again, because this is a strong base, the arrow that we use is the one-hit arrow, represent that sodium ion will not recombine with hydroxide ion to produce sodium hydroxide. Therefore, the sodium ions, which is the conjugate acid of base sodium hydroxide, will not behave as an acid, but it will behave as pH neutral. Here is more comprehensive list of acid-base strength of the conjugate acid-base pair. Now let's take a look at example 1. Provide ionization equation in water of the following ions. Then determine whether they are pH neutral, acidic, or basic ions. First, let's start with reacting sodium ions with water. We see from the previous chapter, water can either produce proton or hydroxide ions. In this case, sodium would not combine with proton because they both are positive charge. They repel each other. Instead, sodium ion will react with hydroxide ions which have the opposite charges. And the product of this process would become sodium hydroxide plus proton. But we just see from the previous page that sodium hydroxide is a strong base. Instead, sodium hydroxide would rather ionize to give off sodium, not stay as a molecule of sodium hydroxide. That means the forward direction would not happen. This means sodium will not react with water, it will just stay as they are. In conclusion, we can say that sodium ion is pH neutral because it doesn't do anything to water. Next, let's take a look at chloride ion. Again, react this chloride ion with water, you will get hydrochloric acid plus hydroxide ions as the product. And hydrochloric acid is one of the 6 strong acids. So that means in this case, hydrochloric acid would rather ionize to give chloride ions and proton than just stay as the molecule. So that means the forward direction would not happen. So that means in this case, we can conclude that chloride will not react with water. That means chloride ions is pH neutral. Things that I want to point out for writing the ionization equation in water is that whenever that you have conjugate acid of the base, the conjugate acid because the name is acid, so that means when you react with water, it should produce an acid or proton. Whenever that you see conjugate base of an acid, then again when the conjugate base react with water, it will always produce hydroxide ions. Whether it's pH neutral or not, that's when you need to look at the product that is produced. If the product produced are strong base and strong acid, that means this reaction will not happen because it's most likely to stay as the ionized ions. Let's pause the video and complete the rest of the ions and resume it again when you finish. Now let's take a look at calcium ion. Calcium ions has 2 positive charge. So that means whenever the calcium ions react with water, it's going to combine with hydroxide ions. But since hydroxide ions has only 1 negative charge, which means that calcium will require 2 of the hydroxide ions. In this case, we are going to react calcium ion with 2 molecules of water. And the product of this reaction would be calcium hydroxide plus 2 protons. Again, because calcium hydroxide is one of the 6 strong base, so that means calcium hydroxide would rather dissociate into calcium and hydroxide ions. It would not stay as the molecule. Therefore, the forward reaction will not happen. In conclusion, calcium ions is pH neutral. For the nitrate ions, when it reacts with water, it will produce nitric acid because it's going to accept proton from water, and another product would be hydroxide ions. Again, nitric acid is one of the 6 strong acids. So nitric acid will completely dissociate into nitrate. Therefore, the forward direction will not happen. In this case, nitrate and water will stay as they are. Therefore, nitrate ion would be pH neutral. Next, fluoride ions. When fluoride ion react with water, it will accept proton from water and become hydrofluoric acid. And another species is hydroxide ions. Again, these 2 are related by 1 proton, so these 2 are conjugate acid-base pair. Same as the previous example as well, all of these are conjugate acid-base pair. Now let's take a look at the conjugate acid-base pair between hydrofluoric acid and fluoride ions. As you see, hydrofluoric acid is not one of the 6 strong acids. That means hydrofluoric acid is a weak acid. Weak acid only partially ionized, therefore the reaction will proceed in both directions. And because the overall reaction, as you see, it will produce hydroxide ions, so we can classify these fluoride ions as basic ion because produce hydroxide ions. Next, when ammonium ion react with water, it will give a proton to water and convert to its conjugate base, ammonia. And another product would be hydronium ions. Ammonia is not one of the 6 strong base, so that means ammonia is a weak base. Weak base only partially ionized, so that means the reaction can happen in both directions. So that means the overall of this reaction, you can see that it's going to produce hydronium ions, which is the identity of the acid. So that means in this case, it's going to produce acidic solution. And we can say that ammonium ion is an acidic ion. For iron ions, you can see that it has the positive 3 charge. So that means it's going to accept 3 hydroxide ions from water. So we need 3 water molecules. And that would become iron hydroxide plus 3 protons. And as you see, iron hydroxide is not one of the strong base. So that means iron hydroxide is a weak base. And weak base partially ionized, so that means the reversible process will happen. So that means in this case, you will end up with the overall reaction that produce proton. Therefore, the iron ion is an acidic ion because produce proton in the solution. For the carbonate ion, when carbonate ion react with water, it will produce hydrogen carbonate, which is the conjugate acid-base pair, and hydroxide ions. The conjugate acid hydrogen carbonate is not one of the strong acids, so this is a weak acid. Therefore, the reversible process will happen. So that means the overall solution will produce hydroxide ions. Therefore, carbonate ion is a basic ion. In conclusion, the conjugate acid of the strong base will not produce proton. Therefore, the conjugate acid will be pH neutral. And the conjugate base of a strong acid will also not produce hydroxide ions in the solution. Therefore, the conjugate base of the strong acid will be pH neutral. Now, if you look at the weak acid and weak base acid pairs, you will see that the conjugate base of weak acid will produce hydroxide ions. Therefore, the conjugate base of weak acid will behave as basic ion. Vice versa for the weak base and its conjugate acid. The conjugate acid of weak base will always produce proton in water or hydronium ions. Therefore, the conjugate acid of weak base will behave as an acidic ion. We are going to use what we learned here on next page when we try to determine the acid and base property of salt. And again, what we are going to see next is that we are going to take a look at when we combine all of these cation and anion together to make salt. And ultimately, we are going to predict whether the salt will produce acidic solution or basic solution or pH neutral solution. Salt are ionic compound that compose of cation and anion, and salt forms when acid react with base. For example, when sodium hydroxide base react with hydrochloric acid, it will produce sodium chloride and water. If you assign the charge for each of these species, you can see that sodium plus will combine with chloride minus, and hydroxide ions will combine with proton. Therefore, sodium chloride and water form from this acid-base reaction. This sodium chloride salt is an ionic compound that composed of cation and anion. And the goal of this section is to determine the property of salt in water. Here we are going to use the previous concept and look at each of these species, each of these ions, whether they are acidic ion, basic ion, or pH neutral ions. Hydrolysis equation represents the equation of the salt ionization in water. For the salt ionic compound of barium bromide, the hydrolysis equation for this would equal to barium ions and 2 bromide ions. Because barium is in group 2A, that's why the barium will become 2 plus, and bromine is in group 7A, so bromine become 1 minus. Let's go ahead write out the hydrolysis equation for the rest of the salt. For iron bromide, the product of dissociation would be iron ion and 3 bromide ions. Next salt, when you do dissociation, you need to first find the cation and anion. In this case, the anion that we know for sure is the chloride ions. So that means it gives the rest of these to be a cation. So that means the dissociation product for this would be, do the same thing for next salt. We know for sure that cation is written first, and we know that lithium is positive, so this would be the cation part. So that means the rest of this would be an anion part. So the product of this salt hydrolysis would be, last salt, the hydrolysis equation would be, note that the hydrolysis equation of the salt need to contain cation and anions. Next, we are going to use the hydrolysis equation to help us determine whether salts will produce acidic solution, basic solution, or pH neutral solution. We are going to use the concept that we learned from the previous page to combine each of these ions with water and see what are the products. Let's take a look at ions from salt A. When barium ions react with water, it will form barium hydroxide and 2 protons. And when bromine ion react with water, it will produce hydrobromic acid and hydroxide ions. The barium hydroxide is a strong base, and hydrobromic acid is a strong acid. Therefore, this reaction will not occur, which means that it will not produce proton or hydroxide ions, which means that both barium ions and bromine ions are pH neutral. Therefore, the barium bromide salt is a pH neutral salt. Next, let's take a look at next salt, which is iron bromide. You can see that if you react the iron ions with water, this is the equation that you will get. And because we already do the analysis for bromide, so bromide ions is the pH neutral. So that means the only thing that would determine pH would be the result of the reaction between iron ions and water. So if you look at the iron hydroxide is a weak base. Because weak base is only partially ionized, so that means the reversible process will happen. So because the reaction can go both ways, so that means the reaction will produce proton. Therefore, this ions is an acidic ion. Therefore, the salt that come from iron bromide would produce an acidic solution. And this is a balanced ionization equation in water of the acidic ion. Let's take a look at the next salt. Okay, so in part C here, so I'm going to use the ions in part C and react them with water. So as you see, as the conjugate acid react with water, these are the species that it will produce. And as you see, the product of this, CH3NH2, is the conjugate base of weak acid. So that means this is going to be a weak base as well. And because weak base is only partially ionized, so that means the reaction will go both ways. So eventually, the overall reaction will produce hydronium ions, which means that this conjugate acid would behave as an acidic ion. And if you look at the chloride ions on the other hand, chloride ions produce hydrochloric acid, which is a strong acid. This strong acid would most likely to dissociate. So that means the forward reaction is not going to occur. Therefore, there will be no hydroxide produced. In this case, we can conclude that the CH3NH3Cl is an acidic salt because it produces hydronium ion in water. And this is the ionization equation in water of this salt. Now let's take a look at example D. When you react lithium ion with water, you are going to get lithium hydroxide and proton. However, lithium hydroxide is one of the strong base. And because strong base is fully ionized, so that means it will actually most likely stay as dissociated form of lithium ion. That means the forward reaction of this is not going to happen. Therefore, the proton ions will not produce. That means the lithium ions is pH neutral. And now if you look at acetate ions, when acetate ion react with water, it will produce acetic acid. Acetic acid is a weak acid, which means that weak acid will be in equilibrium, so that means the reversible reaction will occur. Therefore, the overall reaction for this solution will produce hydroxide ions. Therefore, the lithium acetate salt is a basic salt because produce hydroxide ions. Next, let's take a look at example E. When ammonium fluoride dissolves in water, it will become ammonium ion and fluoride ions. And when we react the ammonium ion with water, it will become ammonia. Ammonia is a weak base. That means in this case, the reaction will go both ways. Therefore, the overall solution will produce hydronium ions, indicate that these ions is an acidic ion. Next, if you look at fluoride ions react with water to produce hydrofluoric acid. Hydrofluoric acid is a weak acid. Therefore, the reversible process will happen and it will produce hydroxide ions eventually. As you see, this salt produces both hydronium ions and hydroxide ions. In order to tell whether this salt will be acidic or basic solution, we will need to determine the relative strength between these two ions. The problem gives us the Ka value of the weak acid HF and the Kb value of the weak base ammonia. And because the ammonia and ammonium ions are conjugate acid-base pair, so that means if we know what is the value of Kb for these, we should be able to find out Ka of these species as well. And because Ka equal to Kw divided by Kb, therefore in this case, you are going to divide 1 times 10 to negative 14 by the Kb value of 1.8 times 10 to negative 5, because again these two are conjugate acid base pair. That's why this relationship applied. And you will get the Ka of ammonium ion equal to 5.6 times 10 to negative 10. We are going to do the same thing for conjugate base fluoride ions. The conjugate base fluoride ions will have Kb in relationship with the Ka of its conjugate acid HF. So that means if you plug the Kb, which is equal to Kw over Ka, you will get 1.0 times 10 to negative 14 divided by the Ka value of its conjugate acid, which is 3.5 times 10 to negative 4. And you will get the Kb of the conjugate base fluoride ions equal to 2.9 times 10 to negative 11. When you compare Ka and Kb value of the ions that compose of salt, you will see that the Ka value of ammonium ions is greater than fluoride ions, which means that the strength of the acid ammonium ion is stronger than fluoride ions. Therefore, the amount of hydronium ions that produce would be much greater than hydroxide ions in this case. So we can conclude that the salt of ammonium fluoride would be an acidic salt because it produces more of the hydronium ions than hydroxide ions. In summary, salt composed of cation and anion. In order to determine the acidity and basicity of the salt, you will need to look at how the cation react with water and how the anion react with water. When both cation and anion react with water and produce strong acid and strong base, then this salt will classify to be a neutral pH salt. However, if salt react with water, the cation produce strong base and the anion produce weak acid, then the salt would become an acidic salt. Next, for the salt that their cation react with water to produce weak base and their anion react with water and produce strong acid, this salt then will classify as a basic salt. And for cation and anion that dissolve in water and produce weak base and weak acid, you will need to use their relative Ka and Kb value to determine acidity and basicity of the solutions. Next, We are going to learn how to calculate pH of the salt solution. Consider the aniline chloride salt. You can see that the chloride ions, when it react with water, it would produce hydrochloric acid. However, because hydrochloric acid is a strong acid, that means chloride ion will not react with water. It will stay as chloride ions because hydrochloric acid would most likely to dissociate completely and stay as chloride ions. So that means if you look at the other species, we can see that this species is not part of the strong base. That means we are going to react this species with water. So I'm going to set up the reaction in water. And the product of this reaction would be this species has more proton to donate to water. That's why therefore it's going to give off proton to water, and then it will produce hydronium ions eventually. Because this cation produce hydroxide ions in the solution, so that means this salt would classify as acidic salt. So that means when you calculate the pH of your calculated value should come out to be lower than 7 to indicate acidic solution. Recall from the previous chapter, in order to find out pH, we need to look at the concentration of hydronium ions at equilibrium. So that means in this case, we need to set up Rice table to solve for the concentration of hydronium ions at equilibrium. The initial concentration of aniline chloride is given 0.233 molar. We will ignore water because not part of the Ka expression. And the concentration of the product would equal to 0 molar. This reaction is 1:1:1 ratio. That means for the change, because we don't know how much it is changed exactly, so we are going to use negative X for the reactant and positive X for the product, because it's in the same ratio 1:1:1. And the equilibrium concentration would be the difference between the initial and the change. Next, you will need to set up the equilibrium constant expression K. And because this K involve hydronium ions or an acid, so that means the K value expression here is going to be Ka. The problem gives us the Kb of aniline instead, not Ka value. So that means first you will need to convert the Kb value of the conjugate base to the Ka value of its conjugate acid first before you can plug into this equation. The relationship between conjugate acid-base pair is constrained by the Kw. So that means if you want to find out Ka, it will equal to Kw divided by Kb. Plug this value in, you will get 2.3 times 10 to negative 5. Next, plug in Ka value and the concentration at equilibrium, and then solve for X. And to avoid the quadratic equation, we are going to use the approximation that the change of X in comparison to the initial change is going to be negligible. So that means we are going to ignore this negative X in comparison to 0.233. Next, solve for X squared and then square root to get just the value of X. And X is the concentration of hydronium ions at equilibrium. Therefore, if you take negative log of the concentration of hydronium ions at equilibrium, you are going to get pH, which equal to 2.64. Again, your answer have to come out to be less than 7 because this salt we just classified that as acidic salt. Now let's take a look at next salt, sodium acetate in example 4. Sodium acetate, if you look at the sodium ions, we already classified these sodium ions. When sodium ions react with water, it's going to produce sodium hydroxide. But because sodium hydroxide is a strong base, that means this will not happen. Sodium will stay as itself and will not react with water to produce sodium hydroxide. So if you look at the acetate ion, on the other hand, acetate ions will eventually produce CH3CO2H in water, which is acetic acid. This acid is a weak acid, that means it's going to react with water. The acetate and acetic acid are weak conjugate acid-base pair. That means if you want to find out the pH of this solution, we'll need to set up Rice table and use the equilibrium constant to calculate the equilibrium concentration and eventually find out the pH of the solution. Let's start with writing the ionization equation of acetate ion in water. This reaction will produce acetic acid and hydroxide ions. The presence of hydroxide ions from this solution tells us that this salt will be a basic salt. So that means when you calculate pH, the pH of this solution should be greater than 7. Next, let's set up the rest of the rice table. The initial concentration of the acetate would be 2.5 molar, and we will ignore water, and the concentration of acetic acid and hydroxide ions at the beginning would be 0 molar. The change, since they all are 1:1:1 ratio, the change would be negative x plus x and plus x for the product. And equilibrium would be the difference between initial and change. Next, write out the equilibrium constant expression for this reaction. Because this reaction produces hydroxide ions, which is the identity of the base, which means that the equilibrium constant for this reaction must be Kb. However, the problem gives us Ka value, not the Kb value, and we can relate it Ka and Kb value in this case because the acetic acid that is given is the conjugate acid of the base acetate that we want to find out its Kb. So that means use the relationship between Ka times Kb equal to Kw to find out the Kb. In this case, Kb would equal to Kw divided by Ka. If you plug in all the value, you will get Kb equal to 5.6 times 10 to negative 10. Then plug in value of Kb and the concentration at equilibrium and use the approximation to solve for x. You will get x equal to 3.74 times 10 to negative 5. The value of x is the concentration of hydroxide ions at equilibrium. When you take negative log of the hydroxide concentration, you will get POH. To obtain pH, you will need to subtract POH from the 14. And you will get the pH of 9.57. To check your answer, this salt is a basic salt from the previous analysis, so that means your pH solution have to come out to be greater than 7. The take-home message for this is that whenever that you see salt that contain cation and anion, you will need to first find out which species, cation or anion, that will react with water. For example, if cation react with water, it will produce hydronium ions, which means that whenever that you want to find out pH, you need to find out the concentration of hydronium ions at equilibrium. But because the Ka is not given, then you can use the conjugate base Kb to find out Ka by using Ka equal to Kw over Kb. Then you can solve for the concentration of hydronium ions at equilibrium and eventually take negative log of this value will give you pH. On the other hand, if the anion is the one that reacts with water, then you are going to produce hydroxide ions, which means that this solution would be a basic solution. Then set up rice table to find out the concentration of hydroxide ion at equilibrium by using Kb. To obtain Kb, you will need to derive it from the given Ka value of its conjugate acid. And again, after you get the concentration of hydroxide ion at equilibrium, then you can take the negative log, which gonna give you POH, and then you can convert that POH into pH. Please practice more of this concept by doing the DIY page 32 and 33. You can work with your peers during hangout session and get help during hangout session and office hours. The answer key will be posted after the hangout session on Moodle. Thank you for watching.